Okay, so today we got going is calculating empirical molecular formulas. And today is the 13th. Okay. All right, so let's go over what the difference between empirical and molecular is first. So empirical and molecular. So what molecular is, it's the ratio of atoms in a molecule. So, for example, you could do like glucose. What's glucose's formula? C6H12O6. So that's like the ratio in glucose. You get 6, 12, 6. So that's the molecular formula of it. If you want to think about it as 6 to 12 to 6 in the molecule glucose. 6 carbons, 12 hydrogens, and 6 oxygens. The difference for empirical is this is going to be the ratio in lowest terms. So the ratio of atoms in lowest terms. So glucose's ratio would be what? What would be the ratio of atoms in glucose in lowest terms? 1 to 2 to 1. And if we wanted to write that out as the formula, it would be CH2O. So empirical is down to lowest terms. What kind of compound is glucose, by the way? Like, we want to use the big overarching titles of things. It's covalent. It's got all nonmetals. So covalent, bond sharing, all nonmetals. Yeah, the whole deal is covalent, so it's covalent. So this is just the same. So this is glucose's formula. This is also glucose's formula. This is the molecular formula. This is the empirical. The molecular one tells you a little more of the story of the compound. So I'm not going to expect you to draw this next thing, but I just want to show you, like, we don't really get a sense of what glucose looks like from this one, but from this one, we can draw glucose. Again, you don't have to draw this. I'm just doing it to show what kind of information you can get from that formula. Doesn't this look like a fun dot picture to draw? Okay, so that's what glucose looks like. It's a ring with a bunch of carbons around it. Anyway, gives a little more of a story. Let's look at another formula. So I've got this compound N2O6. What would it be called? What would the name of this be? Dinitro. Oh, just change the ending of the dinitrogen because we're in the first. Yep. And then what's the hexoxide, dinitrogen hexoxide. Okay, so that's the molecular formula of that. Again, this is a covalent compound. What would its empirical formula be? NO3. So it'd be nitrogen trioxide. So that's covalence. Covalence can have both empirical and molecular formulas. If we got an ionic one, like calcium hydroxide, the empirical formula going to be? It's the same. Yeah, it was a trick question. Yeah, it's the same. It's the same. Ionics, you already got them in lowest terms. When you guys cross the charges, you know why I told you to do ionic compounds, cross charges, and you reduce? You already put them in lowest terms. Ionic compounds are always in lowest terms. It's really like a repeated combination. They call it a repeated crystal lattice. But that's why these things are already in lowest terms. Therefore, the empirical is always the same as molecular. So if you see an ionic, you're not going to ever see a molecular formula. It's going to be the same. Okay, let's actually do the math now. How to figure it out. What you guys are going to get is lab data, and you're going to have to figure out the empirical or molecular formula based on that. So, for example, I've got a substance is 88.8% copper and 11.2% oxygen. What is the empirical formula? Okay, what's the empirical formula? So basically, we want to figure out what these subscripts are going to be, what X and Y are going to be here. So we know we've got 88% copper, 11.2% oxygen, but what's the formula going to be? Here's what we can do. Instead of thinking about having 88.8% and 11.2%, let's pretend that instead we actually have this in AMUs. We'll say we have 100 AMUs. We'll take a percent and turn it into AMUs. So treat the AMU, or the percentages, as a mass. We've got 88.8 AMUs of copper, and we've got 11.2 AMUs of oxygen, atomic mass units. What we can do is then divide them by their masses to figure out the ratio of one to the other. So what you'll plug in here is your molar masses, or not molar masses. I'll start calling that in a second. It's your the mass of that particular atom. So what's copper's mass? Yeah, 63.55. So you put 63.55 AMUs of copper on the bottom, and that tells us how many AMUs are in one atom of copper. So we're doing some unit analysis again. Do the same thing with oxygen. Oxygen's mass is 16.00 AMUs of oxygen in one atom of oxygen. So we're converting AMUs into atoms. Because we want to figure out how many atoms of copper there are compared to how many atoms of oxygen. So somebody's got a calculator. By the way, how many sig figs should be in the answer here? 3. Because since this is lab data, we're saying this is a measurement from lab, the percentage. We'll use that to control the sig figs. Okay, so how many atoms of copper do I have? What's that? Double check that one. 88.8 divided by 63.55. Is that one not working?
Yeah, it's
Broken.
broken or something. I don't know how to fix it.
Uh-oh. Yeah, that's broke. Sad times. You want a calculator? calculator goes down. We get 1.40 atoms copper. And how many atoms of oxygen? 11.2 divided by 16. Yeah, 0.7, 0.700. Now, we don't have whole numbers here. We want to figure out atoms of copper compared to atoms of oxygen. We don't have whole numbers. So what you should do then is figure out take one of them, the smaller one, divide it by itself so you can get at least one of them to 1. So take 0.07 atoms of oxygen divided by 0.70. And since you do that to one, you have to do that to the other. So we have 1 atom oxygen and 2 atoms copper. You might even just still see that and figure that out, right? Because it's basically 14 divided by 7. So what's our formula then? Cu2. Oh, what would be the name of this compound? Copper 1 oxide. Copper's transition metal. Work on the nomenclature. Keep at it. Okay, so that's how we do these. This is how we get the empirical formula. Convert, change the percentage into mass, divide by the mass of each of the atoms, and then compare the atoms to each other to get one of them at least to 1, and that'll do it. Or just divide by the smaller of the two numbers. Okay, let's have you guys try one now. I'm gonna have you do the next one on your own. Yes. I put oxide. Yep. Okay, we've got a substance. And it contains 69.94% iron and 30.06% oxygen. What is the empirical formula? What is the empirical formula? So I would like you guys to take about the next 4 to 5 minutes here to calculate the empirical formula. So have the last problem out next to you. I will tell you there's a little, you might get to a tricky point at the end of this one because it's a little different. But get at least as far as we did last time, and then we'll see if you guys can figure out what to do next. So if it's okay if you get stuck at the end, I'll go over that. I'll let you guys do that. I'm going to get some coffee quick. extra periodic tables? I do in that little box there. I got some of the orange ones. See if you guys, if you get stuck at the end, maybe you can figure out what we have to do. The key is these have to be whole numbers. Don't go around them. I think most of you guys are just about there where I can go over the next stage. So I'm hoping you guys got to this point at least. You got your atoms of iron, atoms of oxygen, right? And then you divide them both by 1.252. With me so far? Okay. And then you got these numbers. You got a 1 here and a 1.5 here, right? How many folks got to this point? Okay. Anybody figure out what we got to do next? Yeah, Ben, what do we got to do? Yeah, we multiply them by 2. We want to get these things to be whole numbers. So the easiest way to get 1.5 to be a whole number is we multiply by 2. These things have to be whole numbers. And what you do to one, you have to do to the other. So we get a 2 for iron and a 3 for oxygen. Therefore, the formula for this compound is Fe2O3. Do you guys see why we had to multiply by 2 here? Yeah, and so sometimes it'll be 2, sometimes it'll be 3, it might be 4. So if I had like, you saw like a 1.33 here, you'd be like, oh, okay. Maybe I have to multiply that by 3 to get that whole number, right? So you have to kind of do some backwards fraction work. Make sense? Okay, how was that? Okay? All right, now I'm going to show you how to do a molecular one. It's almost the same. So, here's our molecular example. A substance is, whoa, I put an 8, is 83.53% everybody's favorite antimony, and 16.47% oxygen. So start out just like you did before, right? Oh, it's like an empirical one. And then this additional piece of information is going to tell you it's a molecular one. It'll say its molecular mass, and sometimes you'll see the question say weight, which is incorrect, is 583 AMUs. What is the molecular formula? So this one's going to be a molecular formula problem. Just so maybe a little note here, just so you guys are looking back at your notes, maybe later on you can say, oh, okay, that's a molecular formula right away. This one's empirical. Okay, step one, you got to figure out the empirical formula of this compound with antimony and oxygen. So I'd like you guys to do that right now. Figure out the empirical formula for antimony, this compound that contains antimony and oxygen. So to do all the molecular ones, you got to do empirical first. Antimony is Sb, correct. It's one of the funny ones. So get that empirical formula. Maybe you're going along the way, maybe you get stuck, or maybe you get it done, double check with a neighbor next to you. See if you get the same thing. If you use the little red periodic table, I will tell you that the numbers are, I don't know if anybody's using these ones right now, the numbers are a little different. So just give you a heads up. Because it comes up on this problem. Again, when you're all done, maybe check out with someone next to you, see if they got similar answers. Okay. So people got to this point here. You got one atom of Sb to 1.5 oxygen, just like the one above. We're going to multiply those both by 2. So we get 2 Sb's and 3 oxygens. Therefore, an empirical formula of Sb2O3. Sb2O3. How are we doing there? Thumbs up? Okay. All right, so the only thing that's going to add now to do molecular formula is we have to look and figure out if the mass of the empirical formula matches the mass of the molecular formula. If it doesn't, we're going to have to multiply by some factor. We want to see if these two numbers match. So, how do you guys calculate molecular mass again, molecular weight? You add them all up. So we got SB2. Oh, whoops. Sorry about that. SB2O3, and what are we going to multiply these by? Their atomic masses. We already looked those up, so that's nice and convenient. We have them up above. And, like you said, total them up. Let's see if that matches our molecular weight. Or, excuse me, our molecular mass. Ugh. Gets me all the time. We get 243.5 for the antimony. And this one we don't even need a calculator for. 48 for the oxygen. For a grand total of 291.5 AMUs. Okay. So that's the molecular mass of the empirical formula. Is that the same as our molecular mass? No. It's not the same as that. So what are we going to do? What do you guys think? Multiply by 2. What I always do with these ones, I just take my molecular mass from above, the 583, I divide it by what I get for my weight for the weight of my empirical formula, and that gives me the factor that I'm going to multiply all the elements in my empirical formula by. So 583 divided by 291.5, I get exactly 2. Sometimes they won't be 100% exact. It'll be close to it. Like it'll be like 1.99 or 2.03 or something like that. And you're in that range. So then, therefore, my molecular formula is multiplied by a factor of 2. So what is it? SB406. Does that make sense? So if it would have been 3 times, I multiplied by 3. And 4 times, multiplied all by 4. By 5, etc. Yes? This number does not have to be either one has to be this one right here. It'd be like, but yeah, it should be real close to a whole number. If you get like 2.5, that's, that wouldn't work because then you wouldn't get a whole number in that final answer. I'm trying to think there would be an instance where that would work. No. Well, there aren't any instances that it's going to work, really. So we don't have to worry about that. Should be a whole number there. Yes, sir.
Above, where you have to divide by the smallest number.
Mm-hmm.
And that, does it matter if you divide by the smallest number or the bigger number?
This one here?
Yeah. Because I accidentally divided by the other number and I still got the same answer.
Because then you got for this one you got 0.5 atoms of Sb compared to 1 atom of oxygen, right?
I got 1 atom of oxygen compared to 0.667 of Sb.
A 0.66. Okay, we have 1 atom of oxygen compared to 0.667 of that. Then you multiply it all by 3, and that still gave you the numbers 2 and 3. Yeah, I guess that should work. I mean, that should work every time still, because you're still looking at the ratio of one to the other. So yeah, that should be fine.
It's just easier if you use the smaller one.
I think, yeah, it's just easier to use the smaller one, because then you're using less odds are you're going to use less decimals. Numbers will be decimals. They'll have more whole numbers. So I think that'll just make it a little easier to work with. That's a good question. Okay, guys, that's it for me talking. The rest is yours to work on worksheet 6. This is not part of the binder check that's right in this upcoming one, but this is going to be part of the binder check for the end before you take the test. So that's what you guys got for today. So go to it.